Hello and welcome to Chapter 5, and in this chapter we're going to talk about the time value of money. We're going to go through future value, present value, finding I and N, annuities, rates of return, and finally amortization. When we're looking at cash flows or money coming in, we can make what is known as a timeline. And we're going to see timelines throughout the class as we go into the next group of chapters. Tick marks occur at the end of periods. Time 0 is today. Time 1 is the end of the first period. And time 2 is the end of the second period. And periods are whatever you make them to be. They can be years, they can be months. Whatever you deem the appropriate amount of time will be your time periods. If we draw out timelines, we could take a look right here. Up first, we have a $100 lump sum payment due in 2 years, meaning in 2 years we're going to get $100. We could have a 3-year $100 ordinary annuity as well. An ordinary annuity is a financial instrument that gives you a payment every year. So year 1, 100, year 2, 100, year 3, 100. This is an annuity. This is paying us $100 a year for the next 3 years. We could also have what is known as an uneven cash flow stream, and we're going to see what causes this later on in the class. We're going to look at various types of cash flow streams. But in year 0, we spend $50, so we have what's known as an outflow. It could be to buy equipment or buy merchandise to sell. And then year 1, $100 coming in. Year 2, $75. Year 3, $50. So that's an uneven cash flow stream. We have an initial outflow, meaning we spend money, and then we have money coming in over the next 3 years. So those are some examples of timelines and why we would use them. So what if we want to find the future value of an initial $100 after 3 years if we're earning 4% per year interest? Finding the future value of a cash flow or a series of cash flows is known as compounding. And future value can be solved by using the step-by-step financial calculator or spreadsheet methods. We will go through all of these, but I would recommend as we go throughout the course, use either a financial calculator or what I would really recommend, Excel spreadsheets. And as we look here, how is this going to work? After 1 year, our future value is present value times 1 plus interest. 2 years, future value of year 2, present value times 1 plus interest to the second. 3 years, present value times 1 plus interest to the third, and those are going to be all of our future values. And after n number of years, present value times 1 plus interest to the n. After 1 year, we'd have $100, 2 years, $108.16, 3 years, $112.49. And this is due once again to compounding. We're making interest on the interest we previously earned. If you wanted to use Excel, this is going to be how I would recommend to do these problems right here. Your function is equals FV. N, or number of time periods, we're going to put 3. Interest per year, 4%. Present value is negative 100. The reason we put negative, it's going to be an outflow, so we have to take that money and put it into whatever this investment is, earning 4% per year. Payment is equal to 0. It's not paying us anything. Certain things we'll look at as we go through the course will be paying us things like bonds and things like that. In this case, we're not receiving any payments, and it's going to solve for future value, which in this case, $112.49. You can also do this in a financial calculator as well, but once again, I would recommend using Excel for all of the computations we do in this course. What would the present value of $100 due in 3 years be if interest is 4%? One thing to remember, money today is worth more than money in the future as long as interest is some sort of positive number, which it is here. So finding the present value of a cash flow or a series of them is called discounting, the reverse of compounding. And the present value shows the value of these cash flows in today's purchasing power. So what's $100 in 3 years worth in today's money? So if we look here, present value is equal to future value divided by 1 plus interest to the third if it's 3 years, which it is here, or 88.90. Using Excel, here's how we would do it. Punch in N as 3 or 3 years, interest 4%. So be sure to put 4% here. Don't just type in 4, put in a percent. Payment is going to be 0. Future value we know is worth 100 in 3 years. And our present value here, once again, 88.90. So here's going to be your formula, equals PV, and you enter it. Rate goes first, 4%. Number of periods would be 3, N is 3. Payment is going to be 0. Future value is going to be 100, and put for type. Excel is going to ask for type. Excel is going to ask for beginning of period or end of period. Generally select the end of period one unless otherwise specified. So in this case, that means when the compounding is happening, so end of period there. So in this case, that's how we're going to enter our Excel formula. Also, as you go through this chapter, when you look on Canvas, you will note I have posted a bunch of demo spreadsheets on these various calculations, and they're located under the Chapter 5 material. What if we want to solve for our interest rate? Well, we can do that as well. So we generally want to use a financial calculator or a spreadsheet. So what annual interest rate would give us 119.10 in 3 years? So we would use Excel. Our formula is equals rate. Number of periods is going to be 3. Interest is going to be 6%. PV negative 100. Future value 119.10. And payment here is 0. And we're going to type all of this in. And once again, the type, we're going to put the end of period here. Now, what if we wanted to solve for N? And remember, N is number of time periods. So if our sales are growing at 10% per year, how long until they double? So in this case, we're going to put our interest per year here as 10%. Present value is going to be 1. Make it negative 1 because, once again, we are compounding. So interest 10, negative 1, future value 2, so they doubled. We spent 1 and now it's 2, payment 0. You could put any number. You could put negative 100 and future value 200. You would get the same answer. And you would get an N here of 7.3. Once again, to do that, you type in your rate, which is 10%, given right here. Payment 0. Present value and future value, just put in something that's going to double. Present value you put in as a negative number, future value a positive number, and type, once again, end of period or choice 0 in Excel. Unless otherwise specified that you have some sort of financial instrument that's doing the interest at the beginning of the period, which we're going to actually look at on the next, starting on the next slide, you generally put type 0 end of period. Now, what if we want to look at annuities? Annuities are a financial instrument that pays you a sequence of payments over an amount of time. And an ordinary annuity is, once again, paying you at the end of the period. So year 0 is right now. Whatever our interest rate is, we're going to get a payment year 1, 2, and 3. We're going to get 3 years worth of payments starting from next year on. Whereas an annuity due, this is one that if you entered it into Excel, you would click the option for not end of period, but beginning. Because an annuity due pays you at the beginning of each period. When you open an annuity due, you get a payment immediately, and then you'll get 2 more here. So it's both give you 3 payments, but how they're structured is different. So if we want to look at things like PV and FV, we're going to look at the next slide. So let's say we have a 3-year ordinary annuity, at 4%. So it's going to pay us $100 payments at the end of each period. There is no PV. What is the future value of this thing? So it's occurring at the end of each period. So if we have a 3-year ordinary annuity, your rate here is going to be 4%. Be sure to put a percent sign. Number of periods, 3 years. Payment, -100. Present value, put 0. And type, you're going to want to put 0, end of the period. And an ordinary annuity is going to be end of the period. As we saw on the previous slide. And you would get a future value here of 312.16. That's the future value of those payments. What if we want to solve for the PV? So if we want to solve for the PV, put 0 for the future value, and we're just going to find the present value. To do this, once again, our rate is still 4%. Number of periods is still 3 years. Our payment is 100. Our future value is going to be 0. And our type, once again, is 0, end of the period. And you would get a PV of 277.51. Since we're getting those payments over the next 3 years, once again, money in today's money is worth less than generally in the future, as long as there's some kind of rate that is positive. So in this case, the $300 of payments is worth in today's money only $277.51. And that's, once again, due to that notion of time value of money. So that's due to that notion of time value of money. Keep that in mind there. Let's take a look at this one here. What if we had an annuity due? So if we had a 3-year annuity due of $100 at 4%, what's going to happen here? $100 payments are going to occur at the beginning of each period. So if you're going to key this into Excel, we're going to enter it the same way. Payment -100, PV 0 because we're finding future value, interest 4%, N is 3. That's the order you would enter it into Excel. But the important thing is now you're going to select where at the end of the formula it says type. You're going to enter type 1. Type 1 means beginning of the period, because remember, an annuity due pays you up front. So the FV and the PV of the annuity due are actually going to be, the FV is going to be higher, the PV is going to be different as well for the annuity due compared to the ordinary annuity. Our FV here is higher on this annuity due than it was for the ordinary annuity. If we look at this one, our PV is going to be a little higher as well. So both PV and FV are larger, so we enter it the same way. Once again, the only difference is when it asks for type, you're going to put 1 beginning of the period. Otherwise, rate 4%, number of periods 3 years, payment is 100, and future value put for 0. Type is going to be the present value, -288.61. The reason it's generally negative is an annuity is going to cost us money to purchase, so that would be the outflow required to get this sequence of payments. That's going to be the present value. And our type here, once again, we put 1, that is beginning of the period. So PV calculations, once again, what is the present value of a 5-year $100 ordinary annuity at 4%? Once again, we could key this just as easily into Excel, or if you use a financial calculator, you would solve for PV in this manner. Excel could easily do it as well. So the present value of a 5-year $100 ordinary annuity at 4% means starting from next year for 5 years, we're going to get a $100 payment. Present value $445.18. So we can key that into both Excel and also into a financial calculator. I would strongly recommend use Excel for all of the calculations in this chapter and chapters to come, but you're welcome to use a financial calculator as well. What about annuities over time? A 10-year annuity, if we look here, with a $100 payment, has a PV of 81109. You're going to get $1,000 worth of payments, but due to that 4% interest, in today's money, it's worth 81109. A 25-year annuity, so you're going to get $2,500 payments. You're going to make $2,500 in payments, but the PV is really only $1,562.21. So the annuity is worth a lot less in today's money than all of the payments will be worth. The reason is it's a much longer duration of time. Annuities are often used as financial instruments to guarantee financial security. For this reason, you can buy them at a lower cost than they're going to pay out over time due to time value of money. So a lot of times people may buy them to guarantee income to family members, or elderly people may purchase them to guarantee some sort of income. Usually they're larger annuities than paying $100 a year. This is just for demonstration purposes. And then there's something known as a perpetuity. And a perpetuity is an annuity that doesn't necessarily have an end date. It is an annuity that will just keep paying. Perpetuities, depending on how they're structured, may last for the life of the person holding it or something like that. How do we find the present value of a perpetuity? It's simply going to be your payment divided by your interest, which in this case would be $2,500. So that $100, they're guaranteed indefinitely. So the present value of that is $2,500 for the perpetuity here. Now, why is compound interest important? We're going to look at that on our next slide. And compound interest is earning interest on interest you've already earned. So every time you make more interest, you're now making money on the money you've additionally made. So a 20-year-old student wants to save $5 a day for retirement, and every year she puts $5 in a drawer. At the end of the year, she invests the accumulated savings, $1,825, in a brokerage account with an expected annual return of 8%. So how much money will she have when she's 65 years old? So in her example, we're going to get a really large amount of money, over $705,000. So since she is 20 at the moment, N here is 45, we're earning 8% interest a year. We don't have a present value because we're starting out. Payment is going to be negative $1,825 in this case, because we're paying $1,825 a year into this investment, and future value is what we're solving for. So if you want to key it into Excel, 0.08 or 8% goes first, 45 for N, negative $1,825 as your payment, and then put 0 as your present value and end of the period. Unless otherwise specified, interest always compounds at the end of the period. Unless it says at the beginning, but almost always it's going to be the end. So she would have over $705,000 by doing this plan of saving $5 a day and then putting it in this account every year if she does that. So she would have over $705,000 by doing this plan. Slide 23, if we want to solve for future value here, if you don't start saving until you're 40 years old, how much will you have at 65? So this investor is going to do the exact same thing, but the N here is changed. It's now only 25. Otherwise, interest, PV, PMT, and FV are all the same. But note the difference in what this investor would have. So that investor would only have $133,000. Now, what if the 40-year-old investor still wants $705,372.75? How much would he or she actually have to pay in? So we can use a formula called equals PMT. And that's the Excel formula to calculate payment. In this case, set N to 25 because we know this person's also retiring at 65. Interest is still 8% or 0.08. PV is 0. Future value is 705,373. That's what we want, the 705,373. And type, once again, put end of period, choice 0, unless otherwise specified. So this investor is going to wind up having to pay in almost $10,000 a year for those 25 years to catch the 20-year-old. The 20-year-old was able to put away only $1,825. This investor would have to put away $9,648.64 to be guaranteed the same amount of money at retirement. So it does pay to start saving early. It does pay to start saving early due to the power of compound interest. The power of compound interest makes it very, very important to start saving early. If we look here, what's the present value of this uneven cash flow stream? One way we could do it is we can find the present value of each of them. We can find the present value of each of them. So we can use PV time period 1, 4% in Excel or in a calculator. We can discount all of these. So 100 back 1 year, 300 back 2, 300 back 3, and negative 50 back 4, and arrive at this PV. Or you can use a function in Excel called equals NPV, or net present value. Equals net present value will also arrive at the same answer. So in a net present value calculation, use 4% as your interest and you put your cash flows in order. So cash flow 1, 2, 3, and 4, we enter all of them in order, or you can enter them in the cash flow register of a financial calculator and hit the NPV button as well. Either way works, but the Excel function is equals NPV. Both of those will arrive at the same answer. It's going to discount all of them in order. If you do use the equals NPV function or your financial calculator, be sure to put the cash flows in the proper order. Number 1 goes first, number 2 goes second, number 3 goes third, and number 4 goes fourth. Don't change up the order or you will get an incorrect answer. It's going to discount them back at the wrong amounts of time. So will the future value of a lump sum be smaller or larger if compounded more often, holding the stated interest constant? The answer is larger. As the more frequently compounding occurs, we're earning interest on interest. Remember, every time we get an interest payment, we earn interest on the new amount. So even if it's very small, even if it's only a few pennies, we're now earning interest on a larger number. So annual compounding, we would arrive with this $100 at $112.49. Semi-annual compounding, the way to find it by hand is divide your interest rate in half. So instead of 4%, we use 2, and double the time periods. Instead of 3 years, 6 semi-annual periods. And by doing semi-annual compounding, we would have $112.62. So not a huge change, but we are going to have more money. We are going to have more money using semi-annual compounding. So using semi-annual compounding, we are going to have slightly more money to the tune of 13 cents than annual compounding. Obviously, this is a more dramatic effect with larger sums of money, but it is important, the notion of compounding. The more periods we can subject our money to compounding, the more money we're going to earn. So nominal rate is the quoted or stated rate that ignores compounding effects. And the nominal rate stated in contracts, and periods must also be given. So 4% quarterly compounding or 4% daily compounding or something like that. So what are the compounding periods here? 4% per year, but how often is it compounded? And the periodic rate is the amount of interest charged each period. So your periodic rate is your nominal rate divided by the number of compounding periods. So M would equal 4 for quarterly. So if it's a 4% rate and it's compounded quarterly, it's 1% per quarter. If it's monthly, it would be 12 dividing by 12. So if we were getting 6% interest and it's monthly compounding, it's 0.5% every month. So that is the periodic rate. So how do we determine what the rate is once we factor in compounding? And that's what's known as the effective rate. So your effective rate is the annual rate of interest actually being earned once we consider compounding. We can solve them by hand, but usually we're going to use a formula in Excel called equals effect. And equals effect is very easy. What do you type in? You type your nominal rate in a decimal or percent format, so you could key it in here as 0.04 or 4 with the percent sign, and then the number of periods. Since this is semi-annual compounding, 2 periods. If it was quarterly, 4, monthly, 12, so on and so forth. So it is going to actually be not 4%, but just simply compounding semi-annually, it's like you're earning 4.04%. Your effective rate is actually going to be higher than the nominal rate due to that compounding. And we saw that before. You would earn more money with semi-annual than annual. Remember, the difference was very slight. It was to the tune of 13 cents, but you were making more money. So it's like you were earning a higher rate of interest. In reality, you should be indifferent between getting 4.04% annual and 4% compounded semi-annually. There should be no difference between 4.04 annual interest and 4% semi-annual interest. What about the importance of effective rates of return? Investments with different compounding intervals provide different effective returns, and to compare them, you must look at their effective returns, EFF or EAR. So simply having different compounding intervals, you're going to get different effective returns. That's why that equals effect formula is very useful, because it'll allow you to compare investments with different compounding intervals, and you can look at their effective returns. If we look here, here's the same 4%. So annual, it's going to be 4%. Semi-annual, as we just saw, 4.04. Quarterly, 4.06. Monthly, 4.07. And daily, 4.08. So simply depending on the amount of compounding periods is going to actually give you a higher effective rate. So if you got an investment and someone gave you the choice of all of the above, annual, semi-annual, quarterly, monthly, or daily, you would want to choose the maximum number of compounding periods. So daily is better than monthly, which is better than quarterly, so on and so forth. It's not a dramatic difference, but it is a better. It's not a dramatic difference, but it is a better rate of return. When is each rate used? So contracts, you sign a contract for a loan or a credit card or a mortgage or something like that, or what's quoted by banks and brokers, that's always the nominal rate. Not necessarily used in calculations or shown on timelines. Your periodic rate is used in calculations and shown on timelines. So if M is 1, your nominal rate is your periodic rate and your effective annual rate as well. So as long as our time period is 1 on our timeline, so the annuity pays once a year, in that case we're going to show the nominal rate because it's the same thing. Effective rate, or EAR, that's used to compare returns on investments with different payments per year, using calculations when annuity payments don't match compounding periods. So that is taking into account compounding periods. What's the effective compounding on future value? So what's the future value of $100 after 3 years with 4% semi-annual compounding, quarterly compounding? So what do? So semi-annual, you divide 4 in half and use 6 periods. Quarterly, we divide 4 by a quarter, so 1%, and use 12 periods instead of 3 years. And here's the difference. 1/12/62 is semi-annual, 1/12/68 quarterly, so slightly more money with quarterly compounding. Can the effective rate ever equal the nominal rate? And the answer is yes, but only if annual compounding is used. So if annual compounding is used, by definition, your effective rate will be your nominal rate. Otherwise, as long as m is greater than 1, your effective rate is always going to be greater than your nominal rate. So as long as there's more than one compounding period per year, you're going to get a higher effective rate than the nominal rate. What if we want to see the future value of a 3-year $100 annuity that's compounded semi-annually? Our payments occur annually, but our compounding occurs every 6 months, so we can't use normal annuity valuation techniques. Even though we're getting payments every year, how do we find its future value? So we can compound each cash flow individually and arrive at a future value of 312.28. So we can compound each cash flow here. Or what I would recommend, break out the Excel. So find the EAR. So use Excel to find your effective annual rate. You could use the equals effect formula or use the hand calculation. Either way, you're going to get 4.04%. I would recommend use the equals effect formula. And then enter it like a regular annuity, just using our modified interest rate. So future value, instead of 4%, we use 0.0404 or 4.04%. Number of periods, the regular 3 years, because now we've modified the rate. Payment -100, future value is what we're finding. Present value 0, and end of the period. And your future value will now be correct, 312.68. So your future value will now be correct at 312.68. So that's going to be the future value of this annuity. Same thing if we want the present value. Once again, use that 4.04%. Number of periods 3 years. Payment 100. Put 0 for the future value and put 0 for end of period when the interest applies, and you'll get a PV of 277.30. So in both cases, we used the effective interest rate in our formula, and that takes into account the semi-annual compounding. And that will work no matter what the period is. Just use the effect formula and put the appropriate number of periods in to get the appropriate effective rate. You can do it by hand once again, but I would recommend use the software here. What if we want to take a look at loan amortization? And I actually have done an amortization schedule in Excel. It's posted right to Canvas, right under the Chapter 5 heading by the slides and the homework assignment and all of that. And I have a sample one posted similar to what they did in this slide. But let's go through how loans work, and that's going to be the last main topic we look at in this chapter. So amortization tables are widely used for things like home mortgages, auto loans, student loans, business loans, retirement plans, and financial calculators and spreadsheets are great at setting them up. So let's say we want to look at a $1,000 4% annual rate loan with 3 equal payments. So first off, we need to find the payment of this loan. So we have all the information. Remember, when you're finding the payment to a loan, future value is always 0, because what's the reason we're paying off the loan? We're paying it off so it's got no value in the end. Once we pay off the loan, it has no future value. So the goal of making payments is to retire the loan or have a future value of 0. If we want to find the payment of this loan, what are we going to put into Excel? We're going to put in 4% interest, 3 years of time. Present value is negative 1,000 because we borrowed that money. Negative 1,000 is the present value. 0 is the future value, and end of the period, once again, unless otherwise specified. It'll return a payment of $360.35. That's what we're going to pay per year on this loan. So how do we find the interest in year one? So the borrower will owe interest upon the initial balance at the end of the first year. Interest is to be paid in the first year, and it can be found by multiplying your beginning balance by the interest rate. $1,000 beginning balance, rate's 4%. We said annual compounding. This is a really simple example. $40 of interest in year one. How much principal is going to be repaid? Principal is how much is coming off the loan, not just the interest. So if we make a payment of $360.35 at the end of the first year, $40 of it goes to interest and $320.35 goes to principal. So in this case, this is a pretty low interest loan. It's only 4%. You can see pretty easily, if you have a very high interest loan, why they can be so difficult to pay off. Because the bulk of your payment in a really high interest loan is just simply going to the interest, and it's not necessarily knocking down the principal of that loan. So things like credit cards, if you pay just the minimum payment on a credit card, you're really never paying very much of the principal off, and you're going to wind up paying a whole lot more than you actually borrowed. So after year one, what's our ending balance? Well, our ending balance is simply your beginning balance minus what came off the principal, or $679.65. Interest does not come off the principal. That just goes to whomever granted us the loan. So only the $320.35 portion of our payment is going to bring the principal of the loan down. So after year one, we now owe $679.65. And once again, $40 of our payment went to interest. The rest of it reduced the amount of money we owe. So we can look here as what is known as an amortization table. So an amortization table shows you what goes on with the loan. So in year one, we start off with a beginning balance of $1,000. Our payment's $360. 40 of its interest. 320 of it is principal. And our ending balance is going to be, this should be $680. This is a typo right here. This one, $680, that should be your ending balance. There is a typo on these slides from the book, so keep that in mind. This ending balance one should say $680. I believe the one I did in Excel is these exact numbers, but it's been done correctly. So our beginning balance in year two is our carryover balance of $680 that we looked at on the previous slide. Payment is at flat $360. Interest is now down to $27. It's 4% of $680, no longer $1,000. $330 of our payment comes off the principal. Ending balance $347. So as you see, as you pay more and more off a loan, more and more of the money is now coming off the principal from our payments than the interest. So when you pay loans, the first batch of payments, the first few years, you're primarily just paying interest. That's why if you ever want to pay a loan down faster, pay additional money. So if your payment was, it's a student loan, let's say, and your payment's $300, if you give $400 instead of $300, that extra $100 is guaranteed to knock off the principal, and it's going to allow you to pay the loan down a lot faster and pay a lot less interest as a consequence. So realize that when loans, you start paying them out the first few years of payments, or depending on how long the loan is, it may be more than a few years if it's a long-term mortgage or something like that. The majority of what you're paying up front is interest. The later we get, now we're paying more and more principal off. In year three, our beginning balance is $347. Our payment's still $360. Only 14 of it is interest. $347 of its principal, and now the loan is retired. If we add up all of our payments, we paid $1,081. $81 of it interest, $1,000 of its principal. So note right here, interest paid declines with each payment as the balance drops, because as the balance drops, the amount subject to interest is going down. What are the tax implications of this? Well, a lot of loans you can write the interest on a loan off your taxes. So student loans you can. A lot of business loans, businesses can write that interest off. The implications are as you pay more and more off the loan, you have less and less interest to write off on your taxes, but you are retiring the loan. And if you do pay ahead, you wind up paying less money. So that's what an amortization table is, and it's showing you how loans work and how what part of your payment is going to interest and what part is going to principal. And I've replicated one of these in Excel, and that is an easily accessible file. It's located right by all of the other Chapter 5 material, right by the slides and the homework assignment, and it's a sample spreadsheet on loan amortization, and you can download it and use it as a study guide. And it, once again, does not have a typo here. This 360 number, that is a typo. That should say 680. It's just a typo. They put the payment number in twice. The ending balance there should be 680. So if we illustrate an amortized payment, where does the money go? So in our first payment, a large chunk of it was interest and then principal. Our second payment, a lot less interest, and our third payment, very little interest, and the majority is principal. So we have constant payments. The payments are the same every year. Most loans are like that. Payments are constant. And the amount going to interest is declining. As you make more and more payments towards the loan, by rule, your interest payments are going to decline, and the balance of the loan is going to decline as well until you hit the requisite number of years and the loan has been retired. It's been paid off. So keep that in mind if you plan on taking out loans or you're looking at one you may already have. That's how your payments are getting broken down, and that's how they are applying to principal and interest. Loan amortization is a very, very important topic. That is going to take us to the end of Chapter 5. And once again, that was the concept of loan amortization.